microphone.
So to finish off this tutorial session, I'd just like to go through question 5 quickly with you all. You can't hear anything. Hello? So yeah, you can hear me now. Excellent. Thanks, Philippa. So to finish off this tutorial session, I'd just like to go through question 5 with you all quickly to really test our beta reduction engines, get them fired up. So first one is we've got lambda x dot x on y. This is a nice simple example. Parameter, and this is the argument. So the beta reduction goes just to y in for x. There. Beta reduction, well, there's naturally, there's nothing to do here, because we can only do beta reduction when we have something of the form of a redex, which means we have to have lambda blah dot blah applied to something. And we just don't have that here. So in normal form. This one, we can substitute. This can be our formal parameter. This can be our argument. So that will go in and give that. And there's nothing further we can do. That's in normal form. This guy, the only redex here is going to be this as the argument going in for this formal parameter x. And this function says that you take your argument which, of course, is the same thing. So this will go on form. This term here is actually, it's sometimes given omega as a symbol because we use it so. Slight variant on omega with one fewer x's. Again, the only redex is to shove that in for x to that, which we've seen how to do that one already. That beta reduces to that guy up there, subject to alpha equivalence. And the last one is another variant on omega. This guy will beta reduce this argument going in for this formal parameter, and it just returns its argument, which is that. And there's nothing further we can do, so that's normal form. Cool, so that was question 5. So we have probably around 20 more minutes, I'd say, of lambda calculus new material. So I'd like to begin this lecture in the same way that I began the last lecture, by just zooming through the slides that you saw in the previous lecture and then running on straight into the new material. So if you remember from yesterday, we saw beta equivalence, and we saw that beta equivalence had to do with these chains of forwards and backwards beta arrows between two terms. But we noticed that by our Russell theorem, we could simplify this arbitrary chain of forwards and backwards beta reductions and phrase it much more simply by saying you just have to see that the two terms eventually converge downstream. And if they do that, then you get a simpler definition of beta equivalence that says, well, like this. We saw that some terms don't have a normal form. We saw that here as well, like omega, which just beta reduces forever. And we saw that some terms sometimes have a normal form and sometimes don't, and it depends on which strategy you use when you're doing your reduction. So this gave rise to the idea of reduction strategies, which basically came into three forms. We could either, at any point, go ahead and redex, apply the function, substitute in the argument, or at any point we could carry on reducing the argument, n, until that's gone down to form, or we could reduce inside the function. And we saw that these three strategies all actually had a name. Call by name was the first one, call by value was the second, the third one didn't have a name because nobody used it. And we saw that the full rules for beta reduction, if you just restrictions on those rules and take away of the rules, then you can actually obtain completely formal versions of reduction strategies. So we saw that call by name was obtained just by getting rid of this rule and getting rid of this rule. We saw that call by value was obtained by, again, getting rid of this rule, but restoring this rule. We saw that you can try out these call by name strategies on little examples. So call by name would take you down this path. Call by value would take you down this path. Whenever the argument of the function is used more than once in the function, then you're better off using call by value because that will take you down to your normal form via a rather quicker route. But it sometimes caused us problems because if the argument didn't terminate when we tried to evaluate it, and if, in particular, the function was never going to use its argument anyway, then call by name is going to terminate. Call by value is going to diverge. It's going to fail to terminate. So there was a bit of a tension between these two sides. We did a bit of bonus philosophy on extensionality, where we introduced an extra rule for saying when two lambda terms, and this basically said things like lambda x dot sine of x is the same. This was called E2 equivalence. And then we made a few remarks on how to prove the Church-Rosser theorem, although really there was a few remarks to prove the Church-Rosser theorem because we didn't get anywhere. But we saw some nice diagrams. In particular, we tried proving the Church-Rosser by doing a single-step diamond, but found that, of course, beta reduction doesn't actually satisfy. So we thought we'd try a multi-step version where we just have the multi-steps on the bottom half of the diagram like this. And although beta reduction has this property, it turns out that you don't actually go from this step to this step in general because of patterns like this, where we saw that if you take one step, then you can reconverge. But if you allowed on the left to take two steps, then you would never converge. So that suggests Church-Rosser is a little bit tricky to prove. Then we had a silly comic, and then we looked at church numerals. And we saw this idea that the number n could be interpreted in the lambda calculus as a function that, intuitively speaking, you could think of as taking what you mean by the successor function and what you element, and then it will apply the successor function the right number of times to whatever you called 0. So the basic property that, that we got from these church numerals was something like numeral of, so n underlined, gave it a successor, and you gave it a 0. This was beta equivalent to applying the successor n times to 0. So this is just a slight notation to that under brace notation I've got over there on the slide. In fact, we could sort of eta reduce this even further. As a z on this side, a z on this side, we could sort of say this is abusing notation a little bit. It'll work out. So this gives you a thing that applies that function n. Because then we saw plus, which had this definition, and we could sort ourselves that this was a reasonable definition. I mean, quite apart from just trying it out on some church numerals to convince ourselves that it worked. We could use this sort of equation here to say, well, look, if we're doing plus of a church, assuming that m is a church numeral and n is a church numeral, then what the plus function is giving us here is m of s and then n of s of z. But using this sort of intuition, we can rewrite, say, well, ns applied n times to z, and ms over here, that's going to apply the successor m times to this. So if you're applying the successor this many times and then this many times again, that's of course the successor applied m plus n times to z. So that's why plus works. And we do a simplification for multiplying. So we've multiplied the bit on the right-hand side of the multiply function. It looks like this. We've got m assumed to be a church numeral. We've got n assumed to be a church numeral. And so this time what we have is the successor applied n times in the bracket, and then applies this successor, this new concept of a successor. It applies that m. So it's that applied m times all on z. And so this looks a bit like an exponential. This, of course, works out being the same. Exponentiation is also doable, so perhaps you could try that out yourself. We also looked at if statements, a form of if statement where the test condition had to be if some church numeral is 0. And so if n is 0, then you evaluate x1, and otherwise you evaluate x2. There. And this was quite a clever trick. Here we used one of those functions that takes its argument but then completely ignores it. So the intuition here was that if n was 0, then it was just going to return x1, because that's being passed in the 0 position. But then our successor is one of those functions that as long as you, which you would do if your number, then it's just going to throw away everything and return you x2. And I mentioned the predecessor function, which I said was a bit tricky. Did anybody manage to work it out yesterday evening? No? Do email me if you get it. But plus and multiply, and this if statement, and I told you also exponential and predecessor, all of these functions are definable in the Lambda calculus. So we can actually pin down a precise concept of exactly when a mathematical function is definable in the Lambda calculus. And it looks like this. So partial function, so mathematical function here, f, that takes, it's a function that takes k natural numbers, and it returns you a natural number, but it's a partial function, so it might be undefined on certain inputs. Okay? So it takes k inputs and gives you one output, all of the natural numbers, possibly undefined. We'll say that that mathematical function f is lambda definable if there exists a closed lambda term, which say, you remember that a lambda term is closed if it has no. There exists this lambda term f such that whenever the mathematical function f, given some mathematical numbers, x1 up to xk, is defined at result y, then that must coincide exactly with the lambda term f, given the corresponding church numerals of those mathematical numbers. That had better be beta equal, so in practice a series of beta reductions will take you down to the church numeral for y. Okay? So that's the correspondence there. And there's also a case for when, in the undefined case. So here, if the mathematical function is undefined, that's the up arrow there, if the mathematical function is undefined for some inputs, then you'd better have the case that the lambda term, again on those church numerals, has no normal form. So it's got to loop forever. Lambda definability provides another string bow of the Church-Turing thesis that aims to capture what the essence of a mathematical function being computable is. So we saw already earlier in the course that you have this notion of a function being computable via a register machine. And you saw that this coincides exactly with a function being computable via a Turing machine. Well, what we've got now is, now we've got the lambda calculus, we've got another concept here of computable functions. These three concepts, or concepts that are not covered in this course, all of these coincide in its essence computable. I want to do a slightly larger example of how you can serious programming in the Lambda calculus. So this is a very large piece of code for a theoretician. It's the whole line. You've probably seen it quite a few times. So factorial of n, just to remind you, if n is 0, then the answer is 1. And otherwise, you do n multiplied by the factorial of n minus 1. Okay. So how can we do? Well, quite a few of these constructs I've helpfully introduced already. So we can get quite far into the problem already. So we could say the factorial function. So this is the lambda calculus edition of this function. Lambda calculus factorial function had better be a function that takes an n. So I've moved the function over to the other side. So it's a function that takes n, and it starts by checking if n is 0, then return 1, or rather Church numeron of 1. And if n is not 0, then return the multiplication of n by the factorial of the predecessor of n. So you see all of these concepts that we saw in the previous slides are all coming together now to make the factorial example. I'll tell you how to do the predecessor, but subject to that, we're almost there. Just got one problem. This is not a proper definition. This is not a definition of the factorial term, because you can't define something in terms of itself. Factorial appears also on the right-hand side, so it's an invalid definition. So how can we fix this? The problem is the definition is recursive. So we've looked at a bit of how to do if statements in the Lambda calculus, but we haven't done while loops, or any sort of looping behavior. So let's look at that now. So we're going to use a term that looks like this. It's quite long, but it has a couple of features that might be familiar. In particular, it's got this pattern here where you take an x, and then you see x applied to x. Some of these terms that sort of reduce to themselves, in a way. And we're going to try and harness that power to give us looping behavior. You see, the clever thing about this particular term is that it has this property, that if you give any lambda term to it, and then you do a couple of quickly, you'll end up with this term, which is m applied to the thing we just had. If you remember from your previous studies, the mathematical concept of a fixed point is as follows, that x is called a fixed point of the function f if it is the case that if you apply the function f to x, you get back x. That's all it is. It's a very simple concept. That is what it means for x to be a fixed point. Okay? And so if you place quality here with beta, then you'll see what we have here. Fix of m is a fixed point of m. Okay? You see, we apply m to fix of m. Okay? That's our x here. And we get back the same thing. We get back x. Okay. Bear that in mind, and we'll go back to the factorial example and see if we can fix things. So the first thing I want to do here with this right-hand side is do a little bit of algebra with it. I just want to rewrite it like this. All I've done is I've taken, so the text is almost the same, but I've taken fac out. What happens here is that if you basically done, so if I now were to substitute fac back in the variable f that I introduced on the front here, f appears here, so the upshot would be that fac would go back into its place there. Okay? So I've done beta reduction in reverse. Why have I done that? Well, it will become clear in a second. You see, what I've got now is a term that is of the form blah and then fac. Okay? So what I've got now is I want fac to be beta equivalent to blah of fac. Okay? We've seen this already. What we're asking then is fac had better be a fixed point of blah. Fac had better be a fixed point of blah. And the magic is this right-hand side no longer contains fac. So it is a valid definition. And you can try that. It still just works. You just plug in, you've got your definition of fac there, so you can plug that in. You've got take the chair, put it in, churn up your beta reduction engine, and you should get 2. Yeah, it's not very interesting. Try it on 3. That would be more interesting. but it all just works. Okay, so we've seen that the Lambda calculus can encode a whole load of things: numbers, arithmetic. We've seen lists, we've seen recursion. You can also do booleans, pairs, tuples, lists, a whole load of things. The world is your oyster. So I just want to finish off then with just a couple more bonus slides, just to give some extra material for talking about at parties or so on. So one of the questions, so one of the nice things about the Lambda calculus, right, is that it's so minimal. All you've got variables, function applications, and functions. Can we go smaller still? Can we get rid of, so yes, that's smaller still. You can get rid of variables. Wow. How do you do that? So if you have this lambda term here, call that S, and call this lambda term K, and then you say that the only terms you're allowed to write now are function application, or S, or K. So in other words, all of your lambda terms have to be of the form SK, SSKK, with lots of brackets in the right places. So we've got rid of variables. And this is the same power as lambda calculus. Wow. Another topic, you might ask, I don't know why you would, but if you were to ask, is the lambda calculus broken? You see, the story here is that, so I've told you several times that the lambda calculus is like the world's simplest programming language. But the thing is, it was invented in 1936, when there wasn't much demand for programming languages. So the thing is, Church, who invented the lambda calculus, what he was after was not a programming language. He was after a new foundation of mathematics. Okay, so his encoding of 0, that wasn't him trying to, all these Church numerals. That wasn't him trying to fit numbers into this minimal programming language. He wanted a new foundation of mathematics that would say that that is 0, that is 1. And he hopes that just with this tiny little syntax, you could build the entire world of mathematics and logic. The lambda calculus has become very successful in a programming language. Unfortunately, as a foundation of all mathematics and logic, it didn't really work out. And the problem is that you can tie yourself up in knots. So if you just find a lambda term called silly, and the idea is it's a function that takes x, and it returns the logical negation of x applied. Okay, now, obviously, this is part of the lambda calculus syntax, but suppose you squint a little bit and just suppose that we have some concept of logical negation, and we'll just throw that in. Then what can happen here is you'll find that silly will very quickly beta reduce to not silly. Okay? Just one beta reduction step. Substitute that in for x, and you get not of that thing twice, so that's the same as not silly. Okay? Very quick. And so if beta equivalence is no longer a concept of when two programs are equivalent, but if you're trying to use beta equivalence as proper sort of logical equivalence, like in logic, you really don't want to be in a situation where a term is equivalent to the negation of itself. Okay? This would be about as bad as saying true is equal to false. Okay? You cannot use this as a foundation of all logic. It's inconsistent. But we can fix this by adding types. So the entire couple of lectures so far has all been about the untyped lambda calculus. Any types at all. Two types to the lambda calculus. You change the syntax just a tiny bit, where every time you have a function that takes an argument, you'd specify its type. Just like in a. And this type, I mean, this type could be inferred, but that's a separate issue. So now we assume that all of these lambda terms will now have a type. And we'll take the simplest notion of types. So we don't want all these integers, booleans, lists, and so on. Let's just keep it really simple. A type is just a thing, or it's a function. So all you have are, you can say that something is a function that takes things to things. You could say it's a function that takes things to functions from things to things. So it's a very, very, very basic type system. It's the simplest I could think of. The thing is, as soon as you do this, you actually restrict yourself a lot. Because the fix function that I showed you cannot be typed. Nor can any of these functions that have this pattern that we've seen several times, where you have things like this. Because if you have to assign a type for x, you cannot for x applied to x. In one of somebody asked me, isn't this a bit weird to be applying with itself? And it is weird. And you can't give a type. X, I mean, x has got to have the same type here and here, right? But if here we say its type is, well, this x, since we're able to pass it as an argument something of type tau, it had better have type tau to something. So we're requiring x to something and also have type tau. But cannot be the same as this type because this is extra arrow and an extra something. You can not is. So this has big repercussions. For one, it stops you defining that silly function that I saw earlier because that uses this trick. So we've now recovered the lambda calculus as a good foundation of logic. Tie ourselves in knots anymore. So that's good. And indeed, typed lambda calculus does form the basis of a lot of logical things. Higher order logic is all based on this stuff. But we've got a problem because we can no longer define our fix function. You see, the fix function, this enabled us to do recursion, but the fix function also used this trick. And if we can't do recursion, so we can't do loops, we're actually no longer. There's no way you. So what can you do? Well, you could just add the fixed point operator as an extra. Let's not try and encode using the existing operators. Let's just say the syntax of the typed lambda calculus, if we want it to be Turing complete and useful, then you'd better allow functions and applications and variables and fix of n. Of course, this complicates the language. It's no longer quite as minimal. And in fact, once you've done that, you might as well add a few more things, pairs, lists, and so on. And before long, functional programming language. So we've sort of come full circle. So that's it. So we've looked at the syntax of the lambda calculus, the semantics of the lambda calculus, what you can do with the lambda calculus, and then a few extra bonus topics as well. So that's everything. Thank you very much. Oh, you've got your predecessor function.
Because we're something that will like apply a successor n times and then apply like an identity to it, right?
Okay, so you're the
Yeah. So we want